I'm very happy to be able to present here in this conference. I will basically talk about a few projects, some research projects, but I will start out talking about a new building actually that we a building project that we were able to do at the National University of Singapore, well, fairly recently. This building is a new building of our School of Design and Environment, which we started using at the beginning of 2019. So slightly more than a year before the pandemic, and we wanted to basically demonstrate and showcase best performances in terms of mainly energy efficiency, and of course also human well-being in this building within our tropical climate of Singapore. So obviously the building, it is Singapore's first new built net zero energy building, and obviously it uses energy. So there's a large overhanging roof, which at the same time shades the southern wall of or facade of the building, that has a huge array of photovoltaic panels, which provides energy to the building. But at the same time, we try to minimize energy use. So it uses an innovative hybrid cooling system in which there is air conditioning, but the temperature of the air coming in is much higher than normally. And the temperature inside of the building is actually kept at around 24 degrees, which is higher than is usually done. So there are fans in the building to make sure that there's enough air circulation so that people feel comfortable even at a higher temperature. And as a result, there is you can open the windows. There is no recirculation of air. It's always fresh air that is being brought in, that is cooled down, as I said, to a higher degree, and then circulated and then go out of the building. So obviously, when we designed this, we didn't have in mind the pandemic, or what could be appropriate. Here you can see a picture of the building. But we recently also received for this building the Wellbuilding certification at the gold level by the International Wellbuilding Institute. And it's the first building in Singapore, and also the first university building in the world to achieve this WELL certified gold. And if you wonder what this WELL certification is, it goes beyond the normal, let's say, sustainable standards in building, such as LEED or Green Mark or green. And it doesn't only look at sustainability in terms of energy, in terms of materials, in terms of the building, but also the well-being of the users of the building. So it looks at thermal comfort, sound, light, nourishment, movement, community, mind, etc. And so it takes a much more holistic approach. And what you could say is, even though, again, this precedes the pandemic, is that designing this building to be energy efficient in a way that is, also considers the humans their ability to open a window, get fresh air, etc., is of course exactly what we are requiring. Buildings that don't have air recirculation are of course much healthier. I mean, ideally we would all be sitting outside, but that doesn't always work. So the conclusion basically to this is that if we keep in mind the well-being of people when we design buildings and our urban environment, that we are most likely already considering buildings that are better in terms of addressing the requirements of the pandemic and the new normal afterwards. And at the same time as we are also renovating our existing 2 buildings. And obviously this is a renovation, it's not a new building. So they won't be quite net zero energy, or even better, positive net energy, as the building, maybe partly because of the pandemic, has been positive net energy so far. But we are applying the same ideas, the same techniques, the hybrid cooling, etc., in order to make this also a sustainable and good, well, environment for the users. So based on that, I'd like to present a few projects that I've been working on and that I think are relevant to address the new requirements and needs to a certain extent. And they are on data integration, energy performance, and pedestrian comfort. So the first is about data integration. It's really about having sufficient data, bringing it together, integrating it so that we can make better informed decisions in design of our buildings and our urban environment. And this project is based on the virtual Singapore project of the Singapore government, in which they developed a dynamic 3D city model and collaborative data platform by collecting huge amounts of data, basically having LiDAR data collected from planes flying over the city, photos from cars driving around, etc., and building this quite nice model, as you can see, with limited semantics. Because of course, deriving this geometry from point cloud data, from photos, doesn't provide a lot of semantical information, except maybe what is a roof, what is a facade, etc. So the idea was to use BIM submissions, BIM models, to enhance this urban city model. Now, in Singapore, BIM submission is not yet obligatory in IFC compatible form. However, obviously, developers, contractors, etc., are using more BIM models. They are becoming more widespread for both compliance checking by government agencies such as the Building and Construction Authority and the Urban Redevelopment Authority, as well as for development. And we were mainly working together with the Housing and Development Board, another government agency that builds all the public housing, which, yeah, a large 80% of the Singapore population lives in public housing, and JTC, which is is also a government agency and the largest industrial developer in Singapore. So the idea basically was to take BIM models, could be in their native BIM format of Revit or ArchiCAD, exporting these to IFC, and then converting them into the city GML model, which is the model, the representation used by Virtual Singapore, so that these models can then be embedded in Virtual Singapore or used for other use cases. And this was a project that we did together with the Ordnance Survey, the mapping agency of the UK. So at first we met with lots of agencies, ones I've already mentioned, Singapore Land Authority, Government Technology Agency, to understand what their use cases might be for this kind of information. What would they be able to do if this information was integrated, available? Based on that, we realized, obviously, that City GML, as the representation it is focused on large-scale urban models and does not allow for all information or all appropriate information that is in a BIM model to be embedded in City GML. But City GML can be extended using application domain extensions. And so that's what we did. We developed one specifically for the conversion of BIM IFC into City GML. The conversion process itself, we used a technique for that is called triple graph grammar. Basically, there are rules that operate on 3 graphs. One graph being the IFC graph. The way a building is represented in IFC is in a graph-based model or representation. The same applies to City GML. And the third graph is a correlation graph, which basically links elements from the IFC graph to elements of the City GML graph. These correlation edges, they remain within the triple graph for the duration of the conversion, so that information that gets added, these correlation edges that can added, can be later relied upon in subsequent rules. So the rules can really build upon one another. And we applied these rules that we developed. We had a set of 25 rules that we applied to 3 buildings. A is a very small example that we built ourselves. B is a still not a real model. It's a model that is provided by Autodesk with Revit as kind of like a test case. And C is a real building. It's a building of the Building and Construction Authority that they provided us the plans, the BIM model basically, that we could test this on. And you can see at the bottom that for each rule and for each building, it lists how many times that rule has been applied. Obviously, the more complex the building, the more times the rules have been applied. And what you can also notice is that basically, I mean, I won't go into the detail, but it can tell you how many columns there are in the building, how many walls there are in the building, because every rule will apply to one of these elements. And here is just a quick video showing how we went from showing the BIM model, converting into the IFC model, and then into the City GML model, or rather in various City GML models, because depending on the kind of use case that you're interested in, there is not a single city GML model that might be appropriate for all, or it would be maybe too heavy. So we've explored different ideas, and we mainly converted to both 3D and 2D city GML models, where the 2D city GML model is specifically useful for indoor navigation, for mobility analysis, etc. Now you may ask, we can do that with the BIM model as well. Surely, you could do an indoor navigation into the BIM model, but integrating this into an urban model would allow to transition smoothly from indoor to outdoor navigation within a single model, even if it's just going from one building to another building on the same campus. So having this ability to integrate data, we can then explore a number of interesting things. The first thing I want to talk about is energy performance prediction. Now, if we want to predict energy performance for buildings, we have two approaches. One is to simulate the building, but a thorough simulation of a building design requires extensive knowledge on the physical system, especially on the mechanisms occurring inside and outside the building geometry. And so it basically requires a detailed building design. It's not something that you can necessarily do very early on. When the building has already been designed and elaborated, sure, it would be interesting to know what kind of energy performance this building will provide. But the question, of course, remains, is this, can we still do something about it if we don't like it? The other approach is to use statistics or data mining. In that case, we don't need to have a detailed design of the building, but we do require a large amount of data to learn from in order to feed this data mining process in order to be able to say something. So what we did in this project is combine the two. Specifically, we looked at energy performance of residential buildings, of the Singapore public housing stock. On the left-hand side, you can see the distribution of public housing over Singapore. And on the right-hand side, you can see the energy use of these buildings. Information on the left is provided, of course, by the Housing and Development Board. The energy information is provided by the Energy Market Authority, and they have this information on building per building, as well as per unit type. So if a building contains both 1-bedroom units, 2-bedroom units, 3-bedroom units, it will also split it out per unit type. So basically what we did is we took a baseline public housing building, which is rather not too difficult because the Housing and Development Board uses standardized floor plans. So the buildings are not all the same, but the floor plans to a large extent are standardized. And so we were able to build this baseline HDB building in sufficient detail, do an energy simulation to gain knowledge of the energy usage intensity, and we feed that into a neural network in which we also feed the real consumption data of the real buildings in Singapore, as well as some urban parameters that we think are appropriate for energy use. And these are green plot ratio, so the amount of green around the building, the number of stories, obviously the height, the floor area ratio, the gross floor area, the sky view factor, and how compact the building is, which of course, I mean, we know these things are important. The question is, how can we identify how important, can we also identify which ones are the more important? So these are some of the results of the study. Energy usage intensity varies by the number of stories. As you can see on the left-hand side, the higher the building, the lower the energy usage intensity over the entire building, obviously. It also varies by the GFA, the gross floor area. The larger the gross floor area, the lower the energy usage intensity, because of course it is per square meter. And so it's not an absolute energy usage, it's a relative energy usage. You can also think that the height of the buildings, newer buildings are higher than older buildings. So more energy efficient buildings will have higher numbers of floors and therefore have lower energy use intensity. And it also varies by building compactness or capacity, which I don't have the diagram here for. And so this gives a possibility to the designers to actually understand, before they make any decisions, what the impact will be of certain decisions on the energy usage intensity of the residential buildings. And the last project I want to talk about is pedestrian comfort in high pedestrian activity areas. And this is, of course, very appropriate with the pandemic, because, well, if only we don't want high pedestrian activity, because that, of course, especially if it's within an indoor environment, would be problematic. But the thinking about the project was that if there's a lot of pedestrian activity, people may become anxious, especially when we're thinking of older people or other people who have more difficulty going around, whether it's just because they have a pram or because they have other things that they have to carry or have to use to move around. And if, take for example, elderly people are too stressed to go out because there are too many people around, especially in this pandemic, and they just stay indoors all the time, that's of course not good for their well-being. In order for them to stay healthy, they have to go out. So the question we asked is, can we measure and interpret pedestrian comfort in high pedestrian activity areas so that we can provide to the authorities the ways to address these issues. This project contained quite a number of parts, but I will just focus on assessing the design features to minimize the impact of crowding. So what we did was we built a parametric model. I mean, we built a model with a lot of parameters so that we could change these parameters to create different kind of environments: outdoor environments, indoor environments, linear environments, junction environments, environments with different materials used, different widths, different heights, etc., etc. And we made, so here is an overview of all the different parameters, design parameters that we took into account. basically width, division, edge conditions, lighting conditions, visibility, floor and ceiling materials, shelter conditions, and obstructions. And we developed images for these and did a survey among a large number of people from Singapore to ask them, look at these two images. If you are passing through here as part of your daily commute, which path would you prefer as part of your daily commute? Every time they just had to say which one they prefer over the other. And then we looked at all this information and analyzed it. And there are, of course, some very obvious results. Like in terms of width, people prefer wider than more narrow, etc. But we also found some interesting things that might not be so obvious. We also did VR demo to test further our understanding. But here are some key findings, and this is on edge conditions. So trends for edge conditions, both indoor and outdoor. And so what you see on the side, is it a closed wall? Is it an open wall? Is it shops? Is it greenery? People prefer open edge conditions, which, okay, very understandable. That provide a connection to the outdoors, to the surroundings, more than edge conditions that provide enclosure or other functionality like shopping or seats. And they want to have the option. What was interesting is that there was a much stronger preference in younger respondents in outdoor environments. And another finding is about lighting conditions. Again, indoor and outdoor. Now, people generally prefer brighter lighting in all conditions. Again, understandable. You know, it's walking around in a dark environment, of course, is not so nice. But what struck was that especially females and older respondents have much stronger preferences, especially in non-crowded conditions, strongly suggesting that it may be to perceived safety. But as it's non-crowded and darker, people might not feel safe. So we provided all this information to the authorities to guide them in their decision-making on both indoor and outdoor pathways for people. So here comes the end of my presentation. And I would just like to take a quick opportunity to inform you about the special issue of the International Journal of Geoinformation on virtual 3D city models. And if you're in any way interested in contributing to this special issue, the deadline is at the end of March of next year. Thank you.